Chapter 15-4, How Ion Selective Electrodes Work. We just saw that you can build yourself a glass that will selectively reject some ions and allow others to pass through. Right? This is how membrane or ion selective electrodes are going to work. A potential difference is created across a membrane that can be measured. There is no change in the solution or actual contact between the solution you're measuring and your electrode. So for example, in this pH electrode, this is the first one that we kind of discovered of these ion selective electrodes when we're all going to be doing the same sort of trick. You have some sort of semi-permeable selective material or membrane or glass or what have you that is going to allow some things to pass and not other things. It is still the most important. We make pH measurements all the darn time out there, from I want to know why are my plants dying? Is the soil acidity too low or too high? And I want to figure out why my aquarium is not doing well. What's the pH in my aquarium? Right? Very simple measurement for us to make, happens all the time. And it's going to rely on a glass membrane. So our pH sensing electrode, really simple. I've got a silver wire, and in that silver wire, I'm going to build up some AgCl. I have a concentration of 0.1 normal HCl. And of course, on that silver wire, you're going to deposit some chloride. You're going to make AgCl. And then I've got this thin glass wall down here. Right? So this top part looks a lot like your silver chloride reference electrode, doesn't it? Because it basically is. And then in here, we've got our solution of 0.1 normal HCl. We've got this thin glass wall. And this is where the business end of things happen. As the HCl ions are in common with AgCl and the H+ on the other side of the membrane. So let's take a more detailed look at what's going on there. They're going to incorporate this ion selective membrane that's going to respond selectively to one ion. We're going to generate a reliable junction potential signal rather than a redox signal. So you're not measuring a reduction in oxidation like you are in electrodes of the first type, where you just have that metal wire in solution. We're not measuring a potential that builds up because of the spontaneous reaction that happens. Here we're actually really measuring a junction potential, but we know what that junction potential is. We're controlling that. So here is our ion selective electrode. It's got some internal reference electrode. That's usually going to be like a silver chloride reference electrode. We have some sort of filling solution. We can have an external reference electrode. We've got our analyte solution, and at that membrane is where the interesting stuff happens. Right? Below the membrane, in our analyte solution, right, we have some cations, we've got some anions. We're going to, this one's looking at valinomycin, where our cation is going to be potassium, R is going to be C6H5 attached to a boron. Right? So we're going to have some stuff in the middle. And what's going to happen is that our analyte solution is going to have positive and negative end to it. Right? Those opposites are going to attract. We're going to build up a junction potential in here in our selective membrane. It's going to allow things to go through. Right? We're going to build up another junction potential on the inner surface of that membrane. Right? And then that filling solution is going to react to that potential that's building up on the inner surface of the membrane. So our membrane is a hydrophobic polymer, and it's got organic solvent that's going to contain R, a hydrophobic anion, so tetraphenyl borate, L, a ligand with a high affinity for the cation, so in this case the valinomycin. It's got a ligand cation complex, so valinomycin that has captured that potassium, and C plus a small amount of free cation. The filling solution inside is going to contain both the cation and the borate. Right, so we have, and when it's dipped into an aqueous analyte solution containing both the cation and the anion, a few hydrophobic cations are going to diffuse from the membrane into the analyte solution. So some of my C's are going to move out. membrane into the analyte solution and the inner solution. Some of the hydrophobic anions are going to remain in the membrane. Our hydrophilic anions are going to remain in the solution, right? So these little A minuses, they're going to stay. The aqueous solution and inner solution become positively charged. The membrane becomes negatively charged. And this is going to create a potential difference that opposes the diffusion of more C plus into the aqueous phase of the inner solution. So if I've got some C plus that's trying to make it from here into here, no problem, but now I can't go into here. The potential difference is measured with internal and external reference electrodes. So we've got this internal reference electrode, and I've got an external reference electrode, and we're going to measure what is that potential difference now between our two electrodes. The potential difference between the outer analyte solution and the inner solution is going to be E outer minus E inner. Our outer potential is going to be our solvation free energy divided by NF times R minus RT over NF times the log of the activity. So what equation does this look like? This looks very Nernstian, doesn't it? Okay. Our solvation energy, the activity of the cation in the membrane and the activity of it in the outer solution. So what is the activity on the membrane? What is the activity in the outer part? Right? We're going to look at this guy's migration into here. Right? So this guy's going to be products over the reactants. Right? Our E cell is going to be our energy of solvation minus NF minus RT over NF times the natural log of the membrane activity over the outer membrane, outside of the membrane, minus the inner potential. Now, this part right here is going to be a constant. Right? We're going to take our log term here and we're going to split it up into two parts. Right? On the outside, that's going to be relatively constant. The inner potential is going to be relatively constant. And this guy over here, our delta G of solvation over NF, is going to be relatively constant. R, T, N, and F are all relatively constant. So really the only thing that is changing is our A0, right? Or our AO, our activity of the outside. So we're going to get our potential as being some constant plus RT over NF times the natural log of A0, and all that can become a constant. So we're going to get our potential is going to be some constant plus 0.0592 over N times the log of A0. So this log of A0 is going to be proportional to our potential. All right, so now let's take a look, and we're going to see the same trick over and over and over again, right? Where you're looking at what is my potential that I'm measuring. It's going to be some sort of constant, right? May involve the temperature, right? And it's going to be the log of A0, right? So as we're looking at this guy as a log, we could look at that as a P function, couldn't we? Right? So it's a loggy term. We can make that into a P function. So let's do that with one particular ion, and that is hydrogen. And we're going to look at the hydrogen pH measurement using a glass. Section 15-5, pH measurement with a glass electrode. So our pH electrode, you can take the membrane electrode and make a cell with a reference electrode, say a saturated calomel electrode, and measure the voltage that correlates to H plus and thus pH. Now, this is what you would do if you had a cell, right? So you could take a saturated calomel electrode over here, right? This guy would be our reference, right? And over here would be our sensing or our working electrode, or indicator electrode. Right? And the reference electrode is a saturated calomel electrode. We can have some magnetic stir, and this is the solution that we're testing. And over here we've got this glass electrode. That's our indicator electrode. Right? We've got a wire down the middle. We've got some heavy-walled glass that's going to kind of support our thin glass membrane. And inside we've got our hydrochloric acid saturated with AgCl solution, right? So you can measure the reaction that's happening over here relative to this reference electrode. Now, this is a two-electrode system. Did the pH probes that you've used ever look like that? No, they didn't, right? You're not going to take two probes and stick them together. Now, if we set our Wayback Machine to 1950, and I can probably find some kicking around the department somewhere where it's made with two different electrodes, right? But the ones we have are a lot more convenient to use than this two electrode system. You still have two electrodes for your pH electrode. It's just that it's what's called a combination electrode. So you're going to take one electrode and you're going to put it inside the other electrode, right? So I heard you like electrodes. We're going to take an electrode and we're going to put it inside your other electrode to make this combination electrode. We still have this glass membrane that's on the outside, right? On the inside, on part of it, we're going to have this reference part. This is the reference part, right? We're going to have some AgCl on a silver wire, right? This is our reference electrode. Part of that reference electrode is going to get hooked up and go to your meter, right? Then you're going to have a temperature sensor. Sometimes you're going to have this one that's kind of optional, right? And then you're going to have the other part of your electrode, which is going to interact with the glass membrane. So on the inside, that's your glass membrane electrode, your indicator electrode. On the outside, this is going to be your reference electrode. So it's a tube within a tube. Right? The typical combination electrode consists of the following three components: an inside AgCl reference electrode with buffered KCl saturated with AgCl. So that's going to be on the inner electrode. This glass membrane, right? This is what's going to do all the work, or permeable, semi-permeable glass membrane, and an outer AgCl reference electrode saturated with both KCl and AgCl, right? Connected by a porous plug or a salt bridge to the analyte solution. So that's what this porous plug here is. It's going to give you a little bit of contact with the outside solution. These leads that are connected to the inner and outer electrons, electrodes are going to go to the pH meter. They're oftentimes going to be in one of those coax cable BNC type connectors where there's a little wire sticking out of this guy. One of those is going to carry one, the other is going to carry the other. You've got some sort of cap. You've got a liquid level in here. You have a liquid level of the inner reference electrode. You have this Ag wire that often goes around it. So we've got an aqueous filling solution of saturated AgCl and KCl. We'll have that AgCl paste suspended between two sides of that folded Ag wire. So this wire here is part of your reference electrode. Right, so that wire that's going around here, this Ag wire, right, this is going to be our reference. It's going to be covered with AgCl. Right, we got that porous plug to allow ions to migrate, and then this glass that is going to do our selectivity for us. A line diagram for that pH electrode as it measures pH, right, is going to look something like this. We've got our outer reference electrode over here. Right, that is just a regular old reference electrode. We got our H plus outside the glass electrode. That's our analyte solution. So we're going to make this guy, we'll maybe highlight this in blue. All right, so this is our H plus outside. That is this, H plus outside. Right, this is our outside solution.